So now we got to talk about electrochemical cells. Electrochemical cells. There are two major types of electrochemical cells. And when I say cells here, so I'm thinking like, your double A cell battery, your triple A cell battery, your D cell battery. That's what I mean by cells here. And so one of your major types are called galvanic cells. Galvanic cells. And a synonym for this is Voltaic cell. It means the same thing. The second major type is called electrolytic. Electrolytic. Cool. These are your two principal types of electrochemical cells. That's it. That's all you got to worry about. Now your galvanic cells, these are spontaneous. Your electrolytic cells are non-spontaneous. Your galvanic or voltaic cells, they're spontaneous, and we use the fact that they're spontaneous to produce electricity. Whereas in an electrolytic cell, it's not spontaneous. You actually have to pump electricity into this to make it happen. You need a power source of some sort to get an electrolytic cell to work. And so they actually consume electricity. So in an electrolytic cell, we actually use electricity to make a non-spontaneous reaction happen. Now going back to the galvanic for a sec, I told you it's spontaneous, so what could you tell me about delta G? It's negative. But you know what? With redox reactions, we usually don't use delta G in this chapter. We could, and we still will, but more commonly, we use voltage. And technically, the real name for voltage, some physics professors would say, that's not a word. If I said, how far it is from me to you, and if I said, how far, what's the meterage between me and you? That's what a lot of people say voltage is. It's measured in volts, but it's actually called potential. So potential and voltage, same thing. We always call it voltage, but the real name is potential. You should know that though. Potential and voltage, same diff. So in this case, we usually talk about the potential instead. And the potential, in fact, let's just give this I'll call it E cell. Turns out, for a spontaneous reaction, delta G is negative, but the voltage, the potential of that cell, is positive. So here E, and sometimes you'll see it as like a squiggly E, like an epsilon or something. Either way, whatever. But it needs to be positive for the reaction to be spontaneous. I need a positive voltage. And therefore, non-spontaneous, you'll get a negative overall voltage instead. Cool. We got some more terminology. So it turns out when you've got an electrochemical cell, you have two electrodes. In every electrochemical cell, you always have two electrodes. And one of the electrodes is where oxidation takes place. One of the electrodes is where reduction takes place. So at one of the electrodes, electrons are lost, and at the other electrode, electrons are being gained. So, and we have names for these. Called anode and cathode. Anode and cathode. So, and more animals. I like Leo the lion says Gurrit deals with animals, and now we have an ox and a red cat. So guess what happens at the anode by definition? Oxidation always takes place at the anode. That's the definition of anode. Guess what always happens at the cathode? Reduction. So you got a couple of different ways you can remember this. Now, has anybody ever seen an ox before? Anybody seen an ox? A couple people have seen an ox. Have you ever seen a red ox? No, never seen a red ox, right? Has anybody ever seen a cat? I hope you all, but have you ever seen a red cat? Not an orange cat like Heathcliff or Garfield, but a red cat. Oh yeah, you have. Every couple of weeks you always see one on the side of the road, guys. Come on. So red cats, I know, it's terrible. So, but you'll never, but I guarantee you'll never ever forget that ever. So, but if you don't want to be so gruesome, anode and oxidation both begin with a vowel. Reduction and cathode both begin with a consonant. So, but one way or another, you have to know the definitions of anode and cathode. Yeah, sorry, cat lovers. All right, now here's the deal. Which electrode loses electrons? The anode loses electrons, because he's where oxidation takes place. Which electrode, therefore, gains electrons? Cathode. The anode and cathode are connected to each other by a long wire. And so the electrons always travel through the wire from anode to cathode. This is true for everything. By definition, it can't work the other way. Electrons always travel through the wire from anode to cathode. If you want, that's alphabetical order, A to C. So, but it's by definition, it has to go. Electrons are lost and are transferred to where they're gained. It has to work that way. In the universe, if I told you that electrons went from cathode to anode in some crazy battery, you'd say, yeah, and I made a round square. It would mean the same thing. That's totally nonsensical. Electrons can't go from cathode to anode. Because if electrons did go from cathode to anode, then your cathode would really be the anode, and your anode would really be the cathode. So again, electrons, by definition of how we define anode, the place where oxidation takes place, and how we define cathode, the place where reduction takes place, electrons have to go from anode to cathode. The difference then between these two is that where the electrons want to go spontaneously. In the galvanic or voltaic cell, is that where the electrons want to go spontaneously? Yeah. And the reason they do is because the anode is negatively charged and the cathode is positively charged. Cool, that's where the electrons want to go. They want to get to an area of higher potential. That's what electrons want. Whereas over here, though, the charges are switched. The electrons would much rather go this way, but we're forcing them to go this way. How are we forcing them? By pumping electricity into the system, using that energy to force this non-spontaneous reaction to happen. So electrons always go anode to cathode. It's just, do they want to? Is it spontaneous for them to? Galvanic voltaic cells, that's spontaneous. Electrolytic cells, it's non-spontaneous. So the charges are what are switched. Cool. These are your big differences, conceptually, between the two. Notice we can understand these big differences without ever drawing what these look like, but we are going to draw what these lovely electrochemical cells look like as well. So, but this you definitely should understand as your principal differences between the two to start with. If I wanted one of these two, so if we look at my mic here, I just rechanged the batteries. The batteries in my mic here, what kind of electrochemical cell are they? So the two types, the batteries in here, AA batteries. These produce electricity, this uses up electricity. Are these producing electricity or using up electricity? They're producing it. And so batteries, they're your galvanic cells. That's batteries. Cool. Now, however, if I took these batteries and I put them in a recharger, if I had the recharger just sitting on the table here, would it recharge them? No, what would I have to do? Plug it into the wall. And while they're being recharged, it runs everything backwards to recharge them. While they're being recharged, that would actually be an electrolytic cell. It would need a power source like the wall. And so technically, when a battery is being recharged, it's acting as an electrolytic. But that's kind of like not the normal case. Normally, when we think of electrochemical cells, we think of making stuff. So when you like electroplate something in chrome, that's an electrochemical cell, turns out. To electroplate it, and you're actually making elemental chrome, metallic chrome, in the process. So if you look, sodium metal doesn't exist in nature on planet Earth at all. It's got such a low ionization energy that all sodium metal that has ever existed on planet Earth got oxidized immediately turning into sodium ions. And so sodium ions exist on planet Earth all the time. They're in salts all over the Earth. But sodium metal in the zero oxidation state doesn't exist. But if I told you I had sodium metal, I wouldn't be a liar. And I do have some sodium metal. How? Well, nature didn't make it, so we had to make it. And the way we often make it is with an electrolytic cell. We can make stuff using, and usually elements is the biggest thing we'll make, using electrolytic cells. We use electricity to make an element. Making that element is not spontaneous, but I can force a non-spontaneous reaction to happen by pumping electricity into the system. And so technically, recharging a battery is an example of an electrolytic cell, but more commonly, we're actually using these types of cells to make elements. We'll talk more about those a little bit later. All right, let's talk about galvanic cells. Now, what do we know about galvanic cells? They are spontaneous, and they are used to produce electricity. Okay, so if you look, we're going to do a galvanic cell, a voltaic cell made from this reaction. And the E standard is positive, so great, spontaneous under standard conditions. Cool, anode, cathode. In drawing diagrams, technically, we're supposed to put the anode on the left and the cathode on the right, but that's the standard way of doing things, but we don't always follow that standard, but we're supposed to. So technically. So if you're an electrochemist, it would be a big no-no to get this backwards, but well, Gen Chem professors' textbooks aren't electrochemists, so they don't always do that, but technically that's the standard way. What happens at the anode again? Gets oxidized. Who got oxidized? Zn does. He goes from 0 to +2. He lost 2 electrons. So in this case, the electrode itself is the metal. And in the solution below it will be the ions. So I didn't show the phases here, but any metal in its elemental form besides mercury is in what form? Solid. And ions, if there's water around, are typically dissolved and are aqueous. And we expect you to know that. And so in this case, the zinc metal is the electrode. The zinc ions are dissolved in the aqueous solution. So the cathode, what happens at the cathode again? Reduction takes place. And who's getting reduced? The copper ions are. The electrode is made of the metal, and the metal ions are in the solution. Now, technically, we can, in this case, we had metals involved, so we can make the electrodes out of those metals. Technically, a lot of reactions will actually use what we call inert electrodes that aren't even part of the reaction. But in this case, with metals involved, the electrodes themselves are made of metals. And the metal electrodes are connected by what? A wire. And electrons always travel from where to where? From where they're lost, anode, to where they're gained, cathode. And so electrons travel through the wire here from anode to cathode. Thing we already talked about. Cool. If we actually break this up into half reactions here, we can see that the zinc metal is turning into zinc 2+ and losing 2 electrons in the process. On the other side, we can see that copper 2+ is the reactant and is gaining 2 electrons to turn into copper metal. And so we can see the half reaction going on at each of the electrodes. So if we look at what's going on here, in this case, the zinc metal of the electrode itself is turning into zinc 2+, zinc metal to zinc 2+. This electrode is actually dissolving away as this reaction goes. The zinc metal electrode starts losing mass as this reaction proceeds, and you start getting more zinc ions in the solution. On the other side, so when the zinc metal turns into zinc 2+, it loses 2 electrons, and those electrons are shuttled off through the wire. So, and in this case, your anode is negative, your cathode is positive. So that's where the electrons want to go. And those electrons, after they're transferred to the other electrode, they just sit on the surface of the electrode. And they wait for a copper ion to bump into it. And the moment a copper ion bumps into the electrode gives it 2 electrons. And when the copper ion gains 2 electrons, what does it turn into? Copper metal. And it turns out when it turns into the copper metal, because it's in contact with other copper metal, it just bonds to it. And this electrode actually gains mass on the other side. So one electrode's losing mass, one electrode's gaining mass, it turns out. Okay, we got one little problem though. And if I don't fix this problem, this battery is a dead battery. So anybody ever have issues with corroded electrodes? And their car wouldn't start and stuff like that. So one time it was corroded so bad that the entire terminal that hooks up the battery was completely broken, just gone. And so it wasn't connected, and my car wouldn't start because it was an incomplete circuit, right? The circuit has to flow from, one terminal all the way through the car and back to the other terminal because the electricity has to flow in a circle. Right now we have an incomplete circuit, and it's a dead battery. And so the last part of a galvanic cell is something that connects the solutions. It's called the salt bridge. It's called the salt bridge. It's often like a glass tube, and they'll put some sort of gel matrix in there and then fill it full of salt. And one of the more common salts that you'll stick in there is sodium nitrate. And so there's a bunch of sodium ions and a bunch of nitrate ions in there. Have you guys done this lab yet? Cool, you may have some fun doing this lab. Don't touch the sodium nitrate with your fingers, or they'll turn black when you get out in the sun. So I highly recommend not doing that. So use gloves. But we fill the thing full of sodium nitrate. So it turns out, in one way, shape, or form, you can think of this as completing the circuit. However, that's not what they want you to remember its function is. It does, sort of, but they want you to remember that it keeps these solutions neutral. So if we look in this beaker over here, before we started this reaction, we had a bunch of water in the beaker, and what did we put into the beaker itself? Zinc ions. Well, if I told you I had a bottle of pure zinc ions, you could call me a liar. You can't ever have just simply a positive ion in that bottle by itself under normal conditions. If I wanted to pour zinc in there, I've got to pour in some sort of salt ionic compound that contains zinc. And so in all likelihood, I probably poured in, easiest bet is like zinc sulfate. And so there's zinc ions and sulfate ions. They always come together as a salt. And so same thing on the other side, I probably added like copper sulfate or copper nitrate or something. And so the solution's got both cations and anions. And for every positive charge, there's a negative charge. And it's perfectly balanced out. But we got a problem. Because what's going to happen to the concentration of cations, positive charges, as this reaction proceeds? Well, we're producing more and more zinc 2+ as this reaction goes. And so in this case, we're going to get more cations. And we'd have an imbalance. There'd be more cations than anions as this reaction goes. The salt bridge keeps that from happening. Anions from the salt bridge travel to the anode. It makes it easy to remember. Anions travel to the anode. For every cation you produce, we'll have an equivalent amount of ions charge-wise coming in to keep that solution neutral. On the other side, in our cathode in this case, what's happening to the cations here? They're getting used up. It's a reactant. The cations on the cathode side, they're being used up. And so initially, we have, for every cation, there's an anion. It's a perfectly balanced solution in charge. But as the cations get used up, we're not going to have enough cations. We're going to have way more anions. To keep that from happening, cations flow into the cathode compartment. Again, makes it easy to remember. Cations flow to the cathode. And it keeps the solutions neutral. Sometimes we say it maintains electrical neutrality in the solutions. That's what the salt bridge does. If you focus, though, where do the electrons travel in the wire? From where to where? Anode to cathode. And electrons have what charge? Negative. And that's electricity, right? Electricity is flowing electrons. Well, notice where the negative ions flow. Electrons go anode to cathode, negative ions go from the cathode direction to the anode. And I kind of like to think of that as completing the circuit. Without that salt bridge, nothing happens. You're not going to get a single thing. Dead battery. The salt bridge, in some sense, completes the circuit, but again, the thing they want you to remember is that it maintains electrical neutrality in the solutions.
Now, what material is the salt bridge made of?
Again, it's like a glass tube, and they'll fill it with like a gel, so it's not like an empty tube, but it's got like a gel in there, and then they fill it full of some sort of salt. Sodium nitrate's a pretty common salt they'll fill it full of.